All right, I finished my general announcements and we're ready to get rolling. We're going to pick up right where we left off with problem 2.112. It says, recall the company that collected data on the height of a particular plant modeled using the normal model centered on a mean of 50.9 with a standard deviation of 10.8. Remember that one tiny little thing is shape, center, and spread all in one. The capital N means unimodal and symmetric. It stands for the word normal, but normal means unimodal and symmetric. Okay, so if, by the way, just side note, if you ever say that distribution is normal and skewed left, you just showed that you don't understand either of those terms because normal means unimodal and symmetric. How can something be normal and skewed at the same time? Can't be. Okay. In any case, use this model to estimate the proportion of plants you would expect to fall within each indicated height range. Let's start with the easy stuff before I get to this actual problem. Okay. What percent of plants should you expect to be between 41 and 61 centimeters? 68%. This is what standard deviation tells you. It says about 2/3 of plants, and this is true for every normally distributed population in the world. About 68% of the population exists within one standard deviation of the mean. What percent of plants are between 29.3 and 72.5? 95. These are numbers we need to have burned into our brain, folks. Okay, it's why it's sometimes referred to as the empirical rule, but more often referred to as the 68, 95, 99, 7 rule, because those numbers are so critical to have memorized. So if I asked you what percent of plants are less than 61.7 centimeters, please understand there are multiple ways of doing this. Okay, for example, let me show you, I'm going to show you in a moment my preferred method, but first let me show you a method that I think is slightly more complicated. And this is just to prove to you, I don't care how you get it done. Okay, so watch. Here's one way you could do this. This is how much? 68%. That should be the whole room. How much is that? 68%. Now, we still have this lower tail to worry about. If we've already consumed 68% of the curve, how much of the curve is still left over? 32%. Okay. If you've already gotten 68, then you haven't gotten the other 32. Does that make sense? And that 32 is evenly split between the lower tail we want and the upper tail we don't want. Does that make sense? So you take 32, you cut it in half. What's half of 32? 16. So this tail over here is 16. This chunk in the middle is 68. And if you do 68 plus 16, you get 84. Everybody got it? That is one of the ways you could do it. That's not the way I did it. The way I did it, okay, was this. I said, okay, I want the entire bottom half. That's 50% of the curve. But I also want this sort of squeeze part in between 0 and 1, and that little part there would be half of 68. Does that make sense? So I take the bottom half of 50 and I add half of the other, 68 I haven't gotten yet, and 50 plus 34, half of 68 is 34, by the way, and 50 plus 34 is 84. Okay? So understand that if you're comfortable with these slices, these 68, 95, 997 slices, you can answer this entire page relatively efficiently, and there's not one right way to do it. There's plenty of other ways to do it. Okay? All right. So I'm going to put a 5-minute timer on the board because there are 5 other questions. Okay. Actually, technically, there are 3 others because the last one is create your own. Okay. And every minute, I'm going to pause the timer and go through the problem that's next. Feel free to work together, folks. Go. Okay, so it's been a minute. I'm going to share with you my preferred strategy that doesn't make it right. What I did to figure out what percent of the curve is at least 29.3 was I did this. I said, I want the middle 95. That doesn't include the upper tail I still want. I want the middle 95 plus half of what's remaining. Does that make sense? So I want the middle 95, but then there's an extra 5 left over, and I want half of that extra 5. Okay? So what I did was 95 plus half of what's left, and that got me 97.5. That's not the only way you could do it. There are other ways you could get it done. I showed one of those alternative methods in green, but again, do what makes sense to you. So that was your minute. I've highlighted on the screen the slice that we want. My method might be far from whatever your preferred method is, but I took advantage of the fact that there are two slices that we can find the distance between. Okay, so let me kind of explain my preferred method. Common wrong answer, by the way, is 2.5%. If you said 2.5%, then you were including this end little micro tail that you should not have been including. So if you said 2.5%, you went beyond the 3 standard deviation marker. Okay, so here, this was my strategy. Okay, I said this distance is 99.7%. And this distance, I'm going to code it red because I want to subtract it away, is 95%. So if I take 99.7 and I subtract away the 95 in the middle, what I'm left with is the two like kind of partial tails that are left between the two. Does that make sense? But I don't want both of them. I only want one of them. So I take that difference and cut it in half. Again, not the only strategy to get this done. Okay, but just sort of what occurred to me first. Now, there are other ways around this. For example, let me show you one other one that's not pre-printed on the page. If you already know that this little micro tail is 0.015, you could figure out this piece. Let me do this in red because it's things you're going to subtract away. You say, I don't want this 0.0015, and this is half of 95, which is 47.5%. So if you take 47.5% and add 0.15% to get 47.5%, and then you realize, well, that's everything in the top half I don't want. Well, then you do 50% minus the 47.65%, and you'll get 2.35%. I didn't have that pre-typed on the board, so if you didn't follow that one, that's not you, that's on me. Okay, but there's, again, trying to push that there's more than one way to get these done. Okay. All right, take another minute, try the next one. All right, so my strategy for part D is going to be really, really similar to my strategy in part C. The only difference is I'm using different markers, okay? So now I'm using the markers between 3 standard deviations out and 2 standard deviations out. That's the difference, okay? So what I did, I'll show my work and then I'll also explain it. Okay, again, a common wrong answer would be 16% because you're including like a fraction of a tail in one direction you're not supposed to. If you said 16%, then you included this little sliver of a tail, which you're not supposed to. Okay, but what I did was I said, this is 99.7, this is 68. So if I subtract the two, what's left is the sum of the two tails in between. Okay, so 99.7 minus the chunk in the middle, 68, leaves me with what's in the middle. And if I cut that in half, I get one of the tails, which is what I'm ultimately interested in. Okay, and keep in mind, let's put these numbers in context. Okay, what's actually happening here is I give you this model to describe these plants, and you're able to say to me, okay, if that really is the model that describes these full-grown plants, then we should expect about 15.85% of these plants to be anywhere from 61.7 to 83.8 centimeters tall. That's insane. The fact that you can be provided a couple numbers, 2 numbers, a mean and a standard deviation, and suddenly you can describe with extreme specificity any percentile range you want. That's what this is doing for us. Okay? All right. Last one says 40 to 83. So again, I'm going to give you all a minute on that. Most of the class seemed to say thumbs up that they were good here. All right, so once again, just showing my preferred strategy. Okay, in this one, I took advantage of the fact. This is actually, if you notice this connection, you could have gotten E done super quickly. We just saw a moment ago that this chunk is 15.85%. The only difference between D and E is I'm including the middle 68. Does that make sense? So all I did was I took my answer from part D and I added 68% to it really fast. Okay, not that that's the only way. There are other ways you could have done this. Okay, the other way that I did it, that's the green, is I said, this is half of 68. and this is half of 99.7. Fine, no problem. You want to do it that way? It's arguably just as fast, and it gets you the same answer. Okay? Questions? Go ahead and turn the page, folks. In a moment, I am going to refer back to our ping chart as well as the normal CDF command. Okay, but let me show you a couple things first. So the top of 2.113, it says fill in the proportions indicated below. Note you should have these memorized. Notice that this says absolute value. Let's make sure we read this notation correctly. The absolute value of z is less than or equal to 1. That means it could be positive 1 or it could be negative 1, but the number can't be bigger than 1. So that first bar is saying you can't be more than 1 away from the mean. You have to be trapped in this range, which is what percent? 68. And the next one within 2 is 95. And the next one within 3 is? Can't hear you. 99.7. Okay, so those are the values we should have memorized. Now, if you have those values memorized, you can do almost all of the Canvas quiz. Okay, however, and by the way, you also could have done all of the previous page. Like the previous page only required being comfortable with the whole number markers. 1, 2, 3, -1, -2, -3. Okay, but we need to be comfortable with the situation where what if we get a z-score, which is nothing more, if you haven't noticed it already, a z-score is nothing more than how many standard deviations from the mean are you. So if you are 2 standard deviations above the mean, your z-score is 2. If you have something that's 1 1/4 standard deviations below the mean, well, then your z-score is negative 1.25. Okay? We have to be able to deal with situations where z-scores are not whole numbers. So we're going to get comfortable with the z-chart. We're going to find these percentiles. We're going to express each as a decimal, and I'm going to show with the calculator as well. Okay? So let me start with the pink chart, with the pink paper, and we're going to start with a z-score of negative 1.5, and then we'll go to positive 2.06, and then I'll give you time to do some yourselves. Okay, so we want to know, it says blank percent, because we're trying to find the percent of the population is below a value with a z-score of negative 1.5. So here's what it's asking us to find. Go to negative 1.5 and take everything under that. Does that make sense? Okay, that's what we're being asked to find. Now, let's see if you all, let me actually talk about a visual strategy before I teach you this real quick. What percent is this? 68. So how much is not in that? 32. So if we were to, and what's half of 32? 16. So if we started here and go down, that's about 16% of the curve. Does that make sense? So the fact that we're starting at negative 1.5, we're starting a little bit lower and going down means whatever it is we're shading better be less than 16%. Does that make sense? Okay. These are mental gymnastics you can go through to sort of anticipate a reasonable answer. Now, it turns out the correct answer, and I'm going to explain how I'm getting this in more than one way. The correct answer is 6.68%. Okay, so as a decimal, it's 0.0668. Now I'm going to show you 2 different ways of doing this. The first way I want to show you is with the pink paper. Now notice the picture up at the top. On one side of the paper, you can clearly see more than half of the curve is shaded in. On the other side of the paper, you can clearly see less than half of the curve is filled in. Does that make sense? That's because if you are below the mean, you are less than 50%. What kind of z-score will you have? Negative. So that's the side where you're looking for negative z-scores. If you flip to the other side, clearly more than half of the curve is shaded. And that's because we're dealing with z-scores that are above the mean. And so we have z-scores that are positive. You'll notice every one of these percentages is above 50%. And on the other side, every one of these percentages is lower than 50%. Now, I already told you the correct answer. Let me zoom in on this. I already told you the correct answer was 668%, which is right here. The question is, why should you be able to know that? So what you do is, for a z-score of negative 1.5, you go down, 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 until you find negative 1.5. Now, here's the problem. The chart's accurate to 2 decimal places. So if I asked you for the percent, like let's say your z-score is negative 1.57, well, then you can't take the first number because that has 1.50 or 1.51 or 1.52 or 1.53 or 0.54, 55, 56, 57. So a z-score of 1.57 leaves about 5.82% under it. But we're looking up exactly negative 1.5, negative 1.50, which is why we take the very first number in the column. Now, I don't expect this to be comfortable the first time you see it, so I will show you another example. Okay, let me show you the next one. And then I'm going to show you how to do this with a calculator. The next one is 2.06. Okay, now 2.06, I can tell so many of you are just ready to work ahead of me. I'm going to ask you to be patient and just slow down. Okay, 2.06 is a little bit past the 2. So we want all of that. Does that make sense? Now, I can anticipate a couple things. For example, how much is that? 95. How much is not in there? 5%. So how much would be just in this lower tail? 2.5%. So if you start at 2 and you go down, 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 if you stop there, that's 95. But if you keep going, you get another 2.5, so you're at 97.5. Everybody does that make sense? So if we start at 2.06, which is a little further to the right, and then we shade down, we should expect something bigger than 97.5%. That make sense? Now, it turns out the correct answer is 98.03%. Let me show you how to get that. On the Z chart, make sure you're on this side of the paper because our z-score is positive 2.06. It's not negative. Okay? So I go to my chart and I'm going to look for 2.0. So I go down, 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 right here. But it's not exactly 2.0, so I'm not going to take the very first number. The columns tell you your second decimal place. I want 2.0, not 1, not 2, not 3, not 4, not 5, but 6. I want 2.06. So I go here and I find 98.03%. Got it? Now, if you prefer to use the pink paper, I kind of like the advantages of this hands-on method. I find that it helps build an intuition about the curve. So if you are finding it's hard for you to kind of picture these things in your mind, and especially the walkthrough of why you should anticipate something bigger than 97.5, if that walkthrough doesn't make sense to you, I would recommend you stick to the pink paper for a little while. Don't go to the automation of the calculator too early. You're going to lose your ability to develop an intuition. Okay? But here's how you do these exact same 2 problems in the calculator, which I would argue is obviously a bit more efficient. Okay? I'm going to start with the negative 1.5. I go to the calculator. I'm going to invite you all to follow along with me, by the way. I want the command normal CDF. There is a command normal PDF. We will literally never use it. We will only use normal CDF. Now, does anyone remember where can you find every command in the calculator? Catalog. The catalog is hidden underneath the 0 key. Notice it's the word blue. The word is blue. At least for me, it's blue. Is it blue on yours? Okay, perfect. So you hit the blue button, the second button, then you hit the 0. That gets you to the catalog. Now, don't spend the next 10 minutes pushing down, 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 trying to get to normal CDF. What button on the calculator also represents the letter N? Log. You'll notice the log key has the letter N next to it. So hit the log button. It jumps you to the ends. And now you can find normal CDF way faster. Okay? Now, here's how the normal CDF command works. If you picture a normal curve and you want to shade from negative 1 point, so here's the middle. Okay, picture the normal curve. I'll do it in the middle of the classroom. Normal curve. Here's the center. And I want to 1.5 down. Okay? By the time you get to like 3, 4, 5, 6, 7 standard deviations out, the amount left in the tail is basically nothing. You got me? So you can tell the calculator, I'd like you to start shading. I'm just going to pick a random number. I want you to start shading at 7 standard deviations back. Because by the time you go that far back, there's basically nothing left anyway. And I want you to stop at negative 1.5. So I'm literally telling the calculator, color in the normal curve, starting at 7 standard deviations back, and go, 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 until you hit negative 1.5. And this should give us the answer we already had, the 6.6%. Beautiful. Now, by the way, I don't do arbitrary numbers like -7. What I do is I'm a bit more extreme, and I just do -99. I do 99. Because if you go all the way back to -99 standard deviations, you literally are at 0 at that point. Okay. So I just it's totally arbitrary. Like even -9 is good enough. Okay. Notice I'll get actually, you can see it's the exact same number. That's actually kind of proof of what I was saying, that by the time you go 7 standard deviations out, the tail is so thin that there's basically nothing there anyway. Okay. Now, what about the other one, the 2.06? Watch this. For 2.06, I'm going to start back at -1 billion. -99 is good enough. And I'm going to tell it to color, 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 go, 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 until you get to 2.06. Now, when I hit enter, I should get that 98 point whatever percent number that we had a moment ago. Now, before I cut you loose, and I tell you to try the other ones yourselves, okay, I'm going to show you a couple other quick examples. So I know many of you are probably chomping at the bit to work ahead of me, but just watch the screen. Let me show you a couple other quick things so that this becomes intuitive for us. If you really understand the normal CDF command, then you should be able to know in your head, don't say it out loud, what this is. Get it quietly. If you have a normal curve centered right here, and you start coloring it in at 1 standard deviation back, you color, 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 and you stop when you get to 1. Now say it out loud. What is that? 68%. Okay. If I had replaced this with 2s, then what is it going to get me? Basically 95. Now, by the way, you're learning that the 68, 95, 997 rule, those are admittedly slightly rounded values. They're not exact, but they're close enough. Okay. Now, let's see if you can follow this one. Don't say it out loud. Don't say it out loud. Raise your hand if you think you've got it. All right, so not a ton of people. So let me do the picture. Picture the normal curve. If you start shading at 0, where is that on the normal curve? Right in the middle, because this represents how far from the mean are you. So if my z-score is 0, I am the mean. My distance from the mean is 0. So I start at the mean, and I color, 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 until I get to 99 standard deviations above the mean, way off to the left somewhere, or in your view, to the right. So now say it out loud. What is this? 50%. Well, 49.9999999%. Okay. All right. Now, this is your chance to get the other 3. I would encourage you to try both the pink paper and the calculator. Okay. So take a few minutes and try to do those in both ways. I'll wait. So I gave students time to complete 2.114. Nobody seems to have any questions, which, hopefully is a good thing and not anybody hiding behind their own misunderstanding. But I think it's interesting to notice the connection between these z-scores and the percentiles. Remember, we're talking about the percent of the curve under that marker. So if I'm standing at 0.67 standard deviations above expected, I'm above 74.86% of the population. But if I go just a tiny bit further to 0.68 standard deviations above the expected, well, then I'm beating a little bit more of the population. And so my percentile jumps to 75.17%. Notice how this links back to the very first lesson of this chapter, which was, what is a percentile? It is the percent of a population you are above. That's what these numbers represent. If that's where you are on the curve, then this is the percent of the population you're beating. That's what that's telling you. Okay. All right. I kind of already gave away the question that's next. Summarize what type of percentile you would expect for positive and negative z-scores. So if I have a negative z-score, what can you guarantee about my percentile? It's what? It's under 50%. And if I have a positive z-score, you can guarantee the opposite. It's above 50%. That's essentially what I'm looking for here. Do you understand that negative z-scores should always result in a percentile less than 50%? And positive z-scores should always result in a percentile greater than 50%. Now, I could flip this script if we were talking about what percent is beating you. You know, if I asked, well, how many, like, this is your score, but how many people did better than you? Well, now, fine. If you're a positive z-score, so you're beating more than 50% of people, well, then the percent of people that are beating you is less than 50%. But hope is intuitively obvious that if you have a positive z-score, you're beating more than 50%, but that means less than 50% is beating you. Okay. All right. I think my timing is kind of perfect because we have 5 minutes and I only wanted to get through part A of number 16. Questions? All right. So this is the first real world. It's kind of a boring context, but this is the first example of putting z-scores to use. Okay. Light bulb brightness is measured in lumens, energy use is measured in watts, and lifespan is measured in hours while the light bulb is on. A daylight bulb has a mean life of 720 hours. So I want you to picture a curve, and I would recommend you draw this now. And yes, you have to be able to draw a reasonable looking normal curve. Okay. If you draw it like this, that is not a normal curve. If you draw it like this, that is not a normal curve. If you draw it like this, that is not a normal curve. If I ask you on a quiz or test to draw a sketch of a normal curve and you give me any of those, you will lose a point. It needs to look reasonable. It doesn't need to be perfect, but it's got to be reasonable. Okay. It should have a clear peak in the middle. So let me draw this in green now with concavity on either side. Okay. So it doesn't have to be perfect, but it should be reasonable looking. All right. So daylight bulb has a mean life of 720 hours and a standard deviation of 20 hours. So I want you to do the best you can to imagine the 1, 2, 3 standard deviation markers and just count out by 20s in each direction. Okay, and by the time you get to 3 standard deviations, you should basically be at the part of the tail that becomes next to nothing. Okay, now I'm going to keep reading. A soft white light bulb has a mean life of 700 hours and a standard deviation of 35 hours. So we draw a curve centered on 700, and we count out in each direction by 35s. So these are the normal curves that, according to what this problem is claiming, these are the normal curves that show you, okay, this is how these types of bulbs tend to behave. Okay, 68% of the time, a daylight bulb will last between 700 and 740 hours. 68% of the time, a soft white light bulb will last between 665, 735 hours. It would be unusual for a daylight bulb to fail in less than 680 hours. But it would be equally unusual, meaning it would be an outlier. It would be equally unusual if a daylight bulb lasted more than 760 hours. Because if you are more than 2 standard deviations from the mean, we consider that unusual. We consider that an outlier. Okay? All right. So rather than rushing the rest of this problem, we're going to stop here. I'd encourage you to at least maybe read those questions prior to class tomorrow, because we are going to finish this problem tomorrow for sure. Okay? But we're going to stop here. Thanks for watching. Have a good one.